Good afternoon and welcome to Hand Wavy Chemistry. Today it's problem time where we answer chemistry questions. The topic for today's questions is Hess's law. Hess's law states that the net energy change associated with a chemical reaction is independent of the reaction pathway. In other words, it doesn't matter how we get from our reactants to the products, the overall change in energy will be the same. A simple example of this involves the use of a catalyst. A catalyst introduces a new reaction pathway with a lower activation energy, so the reaction occurs quicker. But the difference in the energy levels of our reactants and our products remain the same. But we can take it beyond this. We could imagine taking our molecules and pulling them apart into all of the individual elements that made them up, shuffling them round, and then reassembling them into our products. And Hess's law says that doing this will still give us the same net energy change. And the reason this is important is because chemists like to calculate and tabulate the enthalpy of formation for various compounds. The enthalpy of formation is the amount of energy either absorbed or released when a molecule is synthesized from its elements. Another advantage of Hess's law is that it provides a way to calculate the energy change associated with a reaction that would be too difficult to measure, or even the theoretical energy change associated with a reaction that would not normally occur. Let me give you an example with syngas. Syngas is a fuel source primarily comprised of carbon monoxide and hydrogen, and it is formed through the reaction of carbon with steam. Since this is a fuel source, it would be quite nice to know the energy changes associated with its synthesis. However, it's going to be difficult to directly measure this. As we are using steam, we're adding in a lot of heat to the reaction vessel, so how can we say which changes are due to the reaction and which are just there because we are heating things up? Also, I said it is primarily composed of carbon monoxide and hydrogen. There will also be some carbon dioxide produced as well as possibly some methane produced, all of which will have a different enthalpy associated with their formation. Luckily for us, we can use Hess's law to figure this out. We already know that the enthalpy of formation for water vapor is negative 241.8 kilojoules per mole. We also know that the enthalpy of formation for carbon monoxide is negative 110.5 kilojoules per mole. So rather than trying to calculate the energy change directly from carbon reacting with steam, instead, we will reverse the reaction that produced the water vapor. So now our H2O gas will produce hydrogen and oxygen, and from there, we can react to form the carbon monoxide. Because we are reversing the direction of one of those reactions, we need to reverse the sign. So the energy required to go from H2O gas to hydrogen and oxygen is going to be 241.8 kilojoules per mole. We can then subtract the 110.5 kilojoules per mole, which is the energy released when we form carbon monoxide, and determine that the energy change when we form syngas is 131.3 kilojoules per mole. It is an endothermic reaction, so it absorbs that 131.3 kilojoules per mole. So now let's look at a couple of questions like you might find in an exam or quiz related to Hess's law. Our first question is very similar to the syngas example in that we're going to be thinking about the energy it takes to make different compounds from their elements, in order to determine the enthalpy change associated with the reaction of methane with ammonia to produce hydrogen cyanide and hydrogen gas. So in order to answer this question, we need to think about what transformations we need to do to each of the provided equations. For example, the reaction of 1 mole of nitrogen with 3 moles of hydrogen to produce 2 moles of ammonia. This has ammonia as a product. The reaction we're trying to analyze has ammonia as a reactant. So we're going to need to reverse this reaction. It also has 2 moles of ammonia as a product, but the reaction we are interested in only has 1 mole of ammonia as a reactant. So we're going to multiply this line by -1/2, which will flip it and reduce those coefficients to what we're after. So we'd end up with NH3 going to make 1/2 N2 plus 3/2 H2. And the energy change associated with this will now be 45.9 kilojoules per mole. For the next bit of information we've been provided, we have carbon reacting with hydrogen to produce methane. It has methane as a product. Our main reaction of interest has methane as a reactant. But this time the stoichiometry is correct. So we're just going to multiply by -1 to reverse the order of the reaction, giving us methane going to produce some carbon plus 2 hydrogen molecules. And because all we've done is reverse the order of the reaction, all we have to do is reverse the sign for the energy change. So this is going to just be 74.9 kilojoules per mole. And for the final reaction they've given us, it's in the correct orientation, but the stoichiometry is twice what we want. We only want 1 mole of hydrogen cyanide being generated. As written, this generates 2. So we're going to multiply it by 1/2. So we get 1/2 hydrogen plus carbon plus 1/2 nitrogen reacting to give hydrogen cyanide. And the energy associated with this will be 1/2 of what is written there, which is 135.15 kilojoules per mole. And we can now combine all of these equations together. And what we hope is that once we've written it all out, it should simplify and cancel down to the reaction that we were given to begin with. For example, the 1/2 N2 and the 1/2 N2 will cancel out. The same is true for the carbon and the carbon. And once we combine the hydrogen that's on both sides, we end up with 3H2. So now we have exactly what we see up above, where we have methane and ammonia reacting to give hydrogen cyanide and 3 hydrogen molecules. So all that's left is to add together the energy changes, and we will have the enthalpy change for this reaction, which when added together comes to 256.0 kilojoules per mole. Now for our final question. Things are a bit more complicated because we haven't been given the enthalpies of formation. We don't know how much energy it takes to break these molecules down into their base elements. So instead, we're going to have to combine other complete reactions in order to determine what the enthalpy change is for the reaction of iron 2 oxide with carbon monoxide to produce iron and carbon dioxide. Looking at this first reaction, it is the only one where we have both elemental iron and carbon dioxide on the same side of a reaction arrow. And luckily for us, they are also on the product side of the reaction arrow, which is what we want. So this is going to serve as our starting point. But I'm not going to do anything to the various coefficients out the front. Yes, this reaction as written generates 2 moles of elemental iron, and the reaction of interest only generates 1, but I see a lot of 2s and 3s, and I'm concerned if I start dividing by 2 or dividing by 3, at some point I'll be asked to add a half to a third, and I'll make a mistake. So I'm just going to leave it as it is for now. Unfortunately, this reaction doesn't have iron 2 oxide as a reactant. Instead, it has Fe2O3. So we need to do something to get rid of that. Luckily, the next reaction deals with Fe2O3, although it's on the wrong side of the reaction arrow. So we need to reverse this reaction. So we'll start by multiplying by a negative value. But which negative value should we use? Well, it deals with 3 Fe2O3, and the reaction above only has 1. So it would be entirely reasonable to multiply by negative 1/3. However, as I said before, I'm concerned that if we do this, we'll get asked to add a half to a third later on and make a mistake. So instead, what I'm going to do is multiply the very first reaction by 3 and leave this reaction's coefficients alone and just multiply by negative 1. So let's see what it looks like after we apply these two transformations. Looking at these two modified equations, we can see that indeed the Fe2O3s are going to cancel out. However, now our problem becomes that our reaction involves Fe3O4 as a reactant, which is not what we see in the reaction of interest. So once again, we're going to need to get rid of this. Luckily for us, that is what the third equation deals with. It has Fe3O4 as a reactant, so we're going to need to flip it around. It also only deals with 1 mole of Fe3O4, and we're looking to get rid of 2 moles. So we're going to multiply this by negative 2. Now we see that our Fe3O4s cancel out, and that a lot of the other terms cancel out. For example, the CO2s and the carbon monoxides. Simplifying this down so it's not covered in a whole lot of lines and annotations, we end up with 6 iron 2 oxide reacting with 6 carbon monoxide to produce 6 moles of elemental iron and 6 moles of carbon dioxide. And our enthalpy change for this is negative 66 kilojoules per mole. So all we have to do now is divide everything by 6, and we get that the final enthalpy change for the reaction as written up above is equal to negative 11 kilojoules per mole. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a question you'd like to see answered in a future problem time, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.